We've already explored arc length for a two-dimensional curve. Now we want to look at arc length of a curve that is in three dimensions. We can find how far an object is displaced both horizontally and vertically, and we can use what we know about motion in three dimensions to predict where an object might be at some future time t. But the actual distance that's traveled along a trajectory in three dimensions will take a little bit more work. Remember that when we talked about arc length along a curve in two dimensions, we started out by dividing the interval AB into small sections, and then we constructed little right triangles right along the curve, and we approximated the short arc length over this subinterval to be approximately the length of the hypotenuse of each of the triangles. We used the Pythagorean theorem to get the length of each hypotenuse, and then we just added up the length of all the hypotenuses along the interval from A to B. Then, if we increased the number of subintervals that we had and let the width of each of those subintervals get smaller, we were able to express our arc length as an integral given by L is equal to the integral from A to B of the square root of f prime of t squared plus g prime of t squared, and that's all integrated with respect to t. Now if I use the same kind of reasoning but just expand it to three dimensions, I can now construct an integral that will give me the actual distance that an object moves along a trajectory between point A and point B in three dimensions. This just becomes L is equal to the integral from A to B of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. The integrand, the square root of f prime of t squared plus g prime of t squared plus h prime of t squared, is the magnitude of a three-dimensional tangent vector that is specified by the vector r prime of t is equal to the vector components f prime of t, g prime of t, and h prime of t. This allows me to write my integral in slightly shorter form. The integral from a to b of the magnitude of the first derivative of the vector r of t dt will give me the arc length of the entire curve from A to B. Let's work an example. I want to find the length of each curve. The first curve is given by the vector function r of t is equal to the vector components 3t minus 1, 4t plus 5, and 2t for the interval from 0 is less than or equal to t, which is less than or equal to 1. The second curve is given by the vector r of t is equal to the components t squared, t cubed, for the interval from 0 is less than or equal to t, which is less than or equal to 4. For my first curve, I have to take the derivative of my vector function with respect to t, so that the derivative of r of t with respect to t is the derivative with respect to t of each of my vector components. This gives me a vector specified by the components 3, 4, and 2. The magnitude of this derivative of r is given by the square root of the sum of 9 plus 16 plus 4, which is equal to the square root of 29. My arc length is given by the integral from 0 to 1 of the square root of 29 dt. I integrate that and I plug in my limits of integration, and my arc length is the square root of 29. For my second vector, r of t is equal to the components t squared, t cubed for the interval from 0 is less than or equal to t, which is less than or equal to 4. I take the derivative of r of t with respect to t, which gives me the derivative of each of the individual vector components. This gives me a vector specified by the components 2t and 3t squared. The magnitude of r prime of t is given by the square root of the sum of 4t squared plus 9t to the fourth. I can factor out a common factor of t squared, and I get t times the square root of the sum of 4 plus 9t squared. This is my integrand for my arc length. L is equal to the integral from 0 to 4 of t times the square root of the sum of 4 plus 9t squared dt. Now I'm going to make a substitution and let u be equal to 4 plus 9t squared. This means that du will be equal to 18t dt, and it means that my limits of integration will change. The lower limit will be 4 and the upper limit will become 148. My arc length will be given by 1 over 18 times the integral from 4 to 148 of the square root of u du. I do the integration and I get 1/18 times 2/3 times u to the 3 halves evaluated from 4 to 148. This becomes 1 over 27 times the quantity 148 to the 3 halves minus 4 to the 3 halves, and this simplifies to 8 over 27 times the quantity 37 times square root of 37 minus 1. Speed and arc length are going to be associated with each other. If I think about the formula for arc length, I have my arc length is equal to the integral of the magnitude of the first derivative of the position vector. The magnitude of the first derivative of the position vector is the speed. So since the first derivative of the position vector with respect to time is velocity and the magnitude of the velocity is speed, there is a direct relationship between arc length of a curve, where the parameter t represents time, and the speed of an object along that curve. Let's work another example. I want to find the speed of an object on a trajectory given by the position vector r of t is equal to the components e to the t sine t, e to the t cosine t, and e to the t. Then I want to find the length of the trajectory over the closed interval from 0 to the natural log of 2. The first thing I need to do is find the first derivative of my position vector. R prime of t is specified by the components e to the t cosine t plus e to the t sine t, e to the t cosine t minus e to the t sine t, and e to the t. The magnitude of this first derivative is given by the square root of e to the 2t times 2 times the quantity cosine squared t plus sine squared t plus e to the 2t. This simplifies to be e to the t times the square root of 3. I set up my integral for arc length, where L is going to be equal to the square root of 3 times the integral from 0 to the natural log of 2 of e to the t dt. This gives me square root of 3 times e to the t evaluated from 0 to the natural log of 2. I get the square root of 3 times the quantity 2 minus 1 is equal to the square root of 3. This is my arc length for the trajectory between 0 and the natural log of 2. Now you get to try it. Pause the video and find the speed of the trajectory that is given by the vector valued function specified by the vector components 4 sine t, 4 cosine t, and 3t. Then calculate the arc length over the closed interval from 0 to 6 pi. When you're ready, restart the video to check your understanding. In this problem, I'm going to find the speed, which is the magnitude of the first derivative of the position vector, for the position vector that's given by the components 4 sine t, 4 cosine t, and 3t. And then using that speed, I'm going to integrate over the limits from 0 to 6 pi to find the arc length of my curve. R prime of t is specified by the vector components 4 cosine t, minus 4 sine t, and 3. The magnitude of r prime of t is given by the square root of the sum of 16 times cosine squared t plus 16 sine squared t plus 9. This simplifies to the square root of 25, which is just 5. I'm going to compute the integral from 0 to 6 pi of 5 dt, which gives me 5t evaluated from 0 to 6 pi. This gives me 30 pi as my arc length for this trajectory from the point 0 through the point 6 pi. This is how we can calculate arc length in 3 dimensions and relate arc length to the speed of my object along its trajectory. Be sure and let me know if you have any questions.